Hi folks, welcome back to Physics with Captain Rod, making this one here to help you out with number 17 in your Unit 4 homework. Okay, so in 17 we have this, get this working here. We have this system here. And it has these forces applied to it in the form of tensions in those strings. Okay, so let's see. It says find the angular acceleration of the disk. So start by drawing a free body of this object. Now you can go ahead and use this picture, will be just fine, and you can use these forces as two forces in your free body already drawn, that's fine. There are two additional forces that you need to draw in your free body, right? This object has a pretty significant mass. There's one force vector you need to add. And then the other one is coming from the fact that this object is supported. It's not allowed to fall. Right? There is a force applied by a pin onto this object. So you need to put a force vector on that. Now what you call that force vector, that's up to you. Call it whatever you want. I would just call it P for pin force. It's just fine. Right? And that's pretty well it. I can't think of any other relevant forces to put in our free body. Then you're going to write the following equation. Sum of all torques equals I alpha. That's Newton's second law for rotation. Now, as we glance at this, maybe it's clear which way it's going to accelerate, maybe it's not. I don't know if you can tell or not, but if you can't tell, just guess a direction to call positive. So generally speaking, counterclockwise is considered positive. I would just write that equation with counterclockwise positive. Now, when you get your free body done, if you look at it and you are summing torques about the center, that's important. Only two of those forces should be creating torque. Two of them should be going right through the center of the pin. The 150, right, when you calculate the torque, you're going to need this distance. That's the outer radius of this object. Then the torque created by the 200 newtons, you're going to need this distance. That's that inner radius. Right? So this torque equation here on the left-hand side, this should have two terms. Right now, this moment of inertia. Now I know that the way this is worded, like it has an inner and outer radius, this was relevant for the ropes, but at least you notice where I say that the mass is uniform. So basically what that means, right, as far as the disk is concerned, or I'm sorry, as far as this object is concerned, you can treat it as a disk. So look up how to calculate the moment of inertia of the disk and just use the outer radius, right, in that formula. The inner radius doesn't really have anything to do with that. That thing's not hollow or anything like that. And then you're going to just algebraically find the angular acceleration. Shouldn't be all that difficult. Let me take a look at part B. Okay, so part B where it says find the force applied to the disk at the pin. So now go to your free body and write the following equation, right? If we sum up forces in the y direction, that one is going to equal 0. Important to realize why. Because the acceleration is 0. The linear acceleration, like in meter per second squared, is 0. This thing has an angular acceleration in radian per second squared, but the center of mass is not moving or accelerating. So if you write out the following force equation from your free body, you should be able to get that pin force out of it. Part C, find the angular speed of the disk after 5 seconds, assuming all the forces are constant. So if all of the forces are constant, then it stands to reason that the angular acceleration should be constant. And that's equal to change in angular speed over change in time. Right? That's what the angular acceleration is. So that's a number you should have. The 5 seconds is given in the problem. The change in angular speed should be no trouble at all at that point. So hopefully that will get you through this homework problem, number 17. Have a great day.